Welcome to Cambridge IGCSE Physics, Lesson 37.1, Electromotive Force, abbreviated as EMF. This is core content for your physics course. Today we'll explore how electrical sources provide energy to circuits. EMF is a fundamental concept that explains how batteries and generators work. Understanding this concept is essential for your physics studies and practical applications in technology. Let's examine our learning objectives for today. By the end of this lesson, you will be able to first define EMF as electrical work done by a source per unit charge. This means understanding how electrical sources convert energy. Second, know that EMF is measured in volts, the same unit as potential difference. Third, understand how energy is supplied by electrical sources like batteries and generators. These objectives align with Assessment Objective 1, which tests your scientific knowledge, and Assessment Objective 2, which tests your ability to apply concepts. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, electromotive force, abbreviated as EMF, which means the energy supplied per unit charge by an electrical source. Despite its name, EMF is not actually a force but an energy per charge. Second, volt, which is the SI unit for both EMF and potential difference, named after Alessandro Volta. Third, energy conversion, which means changing one form of energy, like chemical energy in a battery, into electrical energy. Understanding these terms precisely is crucial for physics success. Let's explore our first core concept. What is electromotive force? The fundamental definition states that EMF is the energy supplied by a source per unit charge. This means for every coulomb of charge that passes through the source, a certain amount of energy is provided. Mathematically, we express this as EMF equals energy supplied divided by charge, where EMF is measured in volts, energy is measured in joules, and charge is measured in coulombs. A key point to remember, despite its name containing the word force, EMF is not actually a force. It's an energy per unit charge. The diagram shows how an energy source converts other forms of energy into electrical energy, providing EMF to the circuit. Now we examine how to measure EMF. Experimentally, this follows Cambridge IGCSE standards. The standard method uses a high-resistance voltmeter. The apparatus needed includes a voltmeter with high internal resistance, a battery or cell, and connecting wires. The method is straightforward. Connect the voltmeter directly across the battery terminals. The voltmeter reading shows the EMF value. Safety is important. Always check the voltage rating of your equipment matches the expected EMF. The key point is that no significant current flows through a high-resistance voltmeter, so it measures the true EMF without affecting the circuit. The circuit diagram shows the correct connection with the Greek letter epsilon representing EMF. Let's work through our first example. The problem states, a battery supplies 120 joules of energy to 10 coulombs of charge. Calculate the EMF. We are given energy equals 120 joules and charge equals 10 coulombs. We need to find the EMF in volts. Step 1, write the equation. We use the definition of EMF, which is energy divided by charge. Step 2, substitute the values. We write EMF equals 120 joules divided by 10 coulombs. Step 3, calculate. This gives us 12 joules per coulomb. Step 4, state the answer. The EMF is 12 volts since 1 joule per coulomb equals 1 volt by definition. Example 2 applies the same principle differently. The problem is, a battery has an EMF of 6 volts. Find the energy supplied to 5 coulombs of charge. The data shows EMF equals 6 volts and charge equals 5 coulombs. Now we analyze. First, rearrange the equation. From EMF equals energy divided by charge, we get energy equals EMF, multiplied by charge. Second, substitute the known values. Energy equals 6 volts multiplied by 5 coulombs. Third, calculate the energy supplied. This gives us 30 joules. Fourth, state the answer with correct units. The energy supplied is 30 joules. The graph shows the linear relationship between charge and energy for this 6-volt battery. Notice how energy increases proportionally with charge, confirming our calculation. Mathematical skills are crucial in physics. Let's examine 3 key skills for EMF. Calculations. First, Equation rearrangement. When we need to find different variables, we rearrange algebraically, starting with EMF equals energy divided by charge, where E represents energy and Q represents charge. We can rearrange. To find energy, we multiply both sides by charge, giving energy equals EMF times charge. To find charge, we divide both sides by EMF, giving charge equals energy divided by EMF. Second, unit conversion. Remember that 1 volt equals 1 joule per coulomb by definition. Also, 1 kilovolt equals 1000 volts. Third, significant figures. Always match your answer precision to the precision of the given data. If data has 2 significant figures, your answer should too. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, a battery has an EMF of 9 volts. What energy is supplied to 2 coulombs of charge? This tests your ability to use the rearranged equation. Question 2 is intermediate. It states 240 joules are supplied to 20 coulombs of charge. Find the EMF. This requires you to apply the basic definition directly. Question 3 is advanced. The question is, a 1.5 volt cell supplies 45 joules of energy. Find the charge moved. This tests your ability to rearrange for charge. For all questions, remember to show you're working clearly, include units in every step, and check your answers make physical sense. Write your answers now before looking at the solutions. Physics principles power our modern world. Let's see how EMF concepts apply in practice. In technology, smartphone batteries typically provide 3.7 volts EMF, converting chemical energy to electrical energy for your device. The battery's EMF determines how much energy each coulomb of charge receives. In transport, electric cars use battery systems with much higher EMF values, often hundreds of volts, to provide the energy needed for motion. In medicine, cardiac pacemakers use very low EMF sources to provide precisely controlled electrical pulses for heart regulation. These applications show why understanding EMF matters. Career-wise, this knowledge leads to electronics engineering, where you design circuits and power systems, and renewable energy design, where you work with solar panels and wind generators that convert various energy forms to electrical energy. Let's review the solutions. For question 1, the answer is 18 joules. We use energy equals EMF times charge, so 9 volts times 2 coulombs gives 18 joules. This is reasonable for a battery supplying energy. For question 2, we find EMF equals energy divided by charge. 240 joules divided by 20 coulombs equals 12 volts. This is a typical battery voltage. For question 3, charge equals energy divided by EMF. 45 joules divided by 1.5 volts equals 30 coulombs. This represents a substantial amount of charge. Now, exam success tips. First, always show you're working step by step. Even if the final answer is wrong, you earn marks for correct method. Second, include units in every step of calculation. Third, check if your answer is reasonable. If you calculate an EMF of 1 million volts for a household battery, something is wrong. Fourth, when asked to define EMF, state clearly that it means energy supplied per unit charge by a source. Let's summarize today's lesson on electromotive force. The key points to remember are, first, the definition, EMF, is the energy supplied by a source per unit charge. This fundamental concept explains how electrical sources work by converting other energy forms to electrical energy. Second, units, EMF, is measured in volts, the same unit as potential difference. Remember that 1 volt equals 1 joule per coulomb. Third, the formula EMF equals energy divided by charge. This can be rearranged to find energy or charge when needed. For further study, review the relationships between energy, charge, and EMF. Practice rearranging the equation to solve for different variables. The next lesson covers internal resistance, which builds on today's work by explaining why real batteries don't always deliver their full EMF to circuits. Ensure you understand today's concepts before moving forward, as physics builds systematically from these foundations.